You're
There we
recording,
go.
right?
Okay. Hello, everyone, and welcome to our design of a level 1 high power rocket. Uh, this is primarily intended as an introduction to rocket dynamics and open rocket to hopefully give you enough knowledge to build a rocket and get your certification. Um, I guess I assume most of you already know this, but just to clarify, um, getting to actually get your certification, all you have to do is build a rocket and fly it on a level 1 sized motor, um, and have a RSO and a witness sign off. So it's pretty straightforward. Um, and without further ado, uh, it's a brief overview of the stuff we're covering: rocket dynamics, components, construction, and open rocket. Um, so obviously we're starting off with rocket dynamics. So the first thing I wanted to start off with, you guys have all taken physics, so I'm sure you guys recognize a free body diagram. I wanted to go over the forces acting on a rocket. Uh, so obviously, the first thing, it's not really a force. I just have the velocity marked here with the red vector v. Um, in any case, as for actual forces on the rocket, um, the most obvious one is gravity, which, as you all know, acts through the center of mass, which you can see I have marked with the yellow and black marker. Uh, and next, you have thrust. Oh, and I should note, because this gravity acts through the center of mass, there's no moments due to that. Thrust, also, if you built your rocket correctly, it should act through the center of mass as well and also produce no moments. Oh, whoops. I accidentally put my hand on the computer. There's some situations in which your thrust will be off axis and produce moments, like if you just don't align your motor correctly, or if you're doing thrust vector control, which is very much outside of the scope of this PowerPoint. But for our purposes, it does not produce any moments. And next up is the actual aerodynamic forces. And I assume this is something you'll talk a lot more about when you take aerodynamics, but there's kind of two ways of thinking about these forces. You can either think about it as the normal and axial force, which you can see on the left diagram. The normal force acts, well, normal. Actually, did I mismark those? I don't know. In any case, you have one force that acts along the rocket body and one that acts perpendicularly to it. And in this case, the force acting axially doesn't produce any moments because it's straight up and down. And the other force is what produces the moment that I've marked here, M. And yeah, the other way of thinking about it is thinking about lift and drag, which is marked as relative to the velocity vector. So drag always acts away from it and lift always acts perpendicularly to it. Both of these methods it's just different ways of writing the same force, but it's useful to think about. In any case, because the aerodynamic forces act at the center of pressure, which is this like average of where all the aerodynamic forces are acting on your body, typically that'll be very close to your fins, just because they produce the most aerodynamic forces as they should. And that produces a correcting moment M. So in a case like this, you can see in this diagram, the rocket is not pointing in the direction it's moving. And that causes the aerodynamic forces to exert a correcting moment, which will pitch it back towards the direction it's flying. And the actual strength of this moment has a lot of impacts on how your rocket flies, and it's something that you typically have to design around. So going more into that, we're looking at the location of this CG and CP. One of the big effects, one of the key determinants in the actual size of the moment is not only just how strong your aerodynamic forces are, but also the location of your center of mass to your center of pressure. And as you guys know, torque increases with both force and distance. And so having a longer distance produces a higher correcting moment. Another thing to note is because of as you're flying, because your rocket motor is burning and losing mass as it ejects mass out the bottom to produce thrust, in flight, your CG will typically move upwards and your rocket will become more stable. So to kind of relate this to actually how you go about designing a rocket, typically the stability of a rocket, did I skip a slide? No, never mind. I messed something up. The stability of a rocket is basically a measure of the size of that moment arm and indicates how strongly a rocket will correct. So typically it's measured in calibers or cal, which one caliber is just the diameter of your rocket airframe. In any case, as you're actually designing a rocket, you'll typically have to work with where the CG and CP are and change fin shapes, mass distributions, etc., to try and get them to be a good distance away. And to kind of give you an idea of what you should be shooting for, you can see I have right here, if you have a stability of less than 1 cal, that's bad. Your rocket will probably not fly straight and it could be pretty dangerous. I don't recommend. It's a bad idea. Typically, most rockets have a 2 to 4 cal stability. I believe our full scale this year had a 2.9 cal stability. And so that is a good range for like what to shoot for just on an average rocket. Higher than 4 cal can lead your rocket to be overstable, although unlike unlike understability, which is a very well-defined region, overstability has no hard boundary, and the effects depend a lot. It depends a lot more on other design aspects of your rocket, which I'm not going to cover here since there's a lot more on the topic. Maybe in the L2 one though. In any case, the next thing I wanted to cover was just that's how it gets up. Coming down is a lot simpler because you don't have to worry about the orientation of your rocket anymore. The most common and reliable method is parachutes. There are some other methods like streamers or like helicopter recovery, but generally those methods are either more complicated or not as suitable to larger rockets like this. You can get away with a lot more if you have a very small rocket. but in this case, we're designing something to fly on L1 motors, so you'll probably just want to go with a parachute. Typically, that's deployed with a black powder charge, and I know in pretty much every like USLI rocket that we build, we use electronic deployment. So that's using a stratologger, some other altimeter, as you guys have seen on the eBay, and that basically decides when it's detects apogee and fires a charge itself. But another method that is pretty common in rockets of this size is motor deployment, in which a lot of motors have a built-in black powder charge at the top, and so after burnout, it'll smolder for a little bit, some specified number of seconds, before it hits another charge, which will basically deploy a charge on the top of your motor, which you can use to eject parachutes. And that typically on stuff like the USLI rocket isn't necessarily desirable, and we tend to buy motors that don't do that. But it can be pretty good if you want an extra redundant form of deployment, or just I think a lot of the L1s that we fly use that. In any case, for deployment options, you also have single deploy and dual deploy. Basically, the difference being in how many parachutes you use. Typically, for the main advantage of dual deploy being that you can have a smaller parachute so that you descend faster for most of your descent before opening your main parachute to slow down enough to be safe. Typically, with the height these level 1 rockets fly to, you don't need to do dual deploy. And if you're trying to go for the simplest possible like system to get L1, the simplest thing would just be have one parachute that is deployed by a motor charge. So next up, I'm actually going to stop real quick. Does anyone have any questions about dynamic stuff before we keep going? Neat. Okay. Next up, going on to components. One of the things I do want to do is talk about how to go about building a rocket. And I typically, if we were just in school, I would just say build it with AIAA. But I also wanted to point out that you can very much build these L1 rockets like at your own house. And here I've listed some of the benefits of either or. With AIAA, we have all the parts for free, and obviously you get access to the tools at WPI, but obviously you can't do that right now because it's the summer, and it also is very contingent on WPI's reopening plans, and we don't really know what's going on. If you want to build it over the summer, buying all the hardware can get a little bit expensive, especially with like larger multi-use things that would typically get reused, like motor casings. But it's still very doable, and even with just hand tools, it's certainly more effort to cut wood by hand than to use a laser cutter, but there's nothing stopping you. To kind of talk a bit about the parts that AIAA stocks, I just kind of wanted to go through these and talk about what's useful. The AIAA for our body tubes, we typically have we buy from Uline these 3-inch inner diameter craft tubes, which are very cheap, and work pretty great for simple rockets. You do have to be careful because they are a little bit more brittle than some other types of airframe. So you have to be careful with how fast you're hitting the ground. Uh, we also have, I might have this somewhat wrong, but I believe they're 20-inch ogive nose cones. Um, for those of you who don't know, ogive just is a description of the shape of the nose cone. If you're curious, you can look up exactly what ogive means, but it just means it's nose cone shaped in this case. um, and yeah, uh, basically they fit well within the 3-inch diameter ones. Oh, to clarify, that's 20 inches long, not including the shoulder though. Typically for things like fins and centering rings, we'll use 1/4-inch plywood, which for this scale works pretty good. We typically use nylon cord. It's often sold as like, I might have the word slightly wrong, but I think they typically sell as like climbing something. I don't know. Tubular nylon. Thank you. There's various parachute sizes that we have stocked, along with the actual motor hardware, which, to clarify, when I say motor hardware, I'm referring to uh, when you actually get a high-powered motor. Oh, yeah, if you look on Kirsten's camera, you can see she has one of these ogive nose cones. But yeah, the motor hardware, your actual motor, when you buy the motor, it comes in like, a case, but the case itself needs to be put into a casing that's aluminum, because the cases they come in are like, they're not actually rated to like hold all the pressure in. And if you just light them without putting them in a casing, I don't actually know what happens, but it won't work well, and it's probably not a good idea, and certainly not recommended. Um, in any case, yeah. So, and finally, for actually attaching your tubular nylon recovery harness. Oh, I'm realizing I never actually defined recovery harness. Recovery harness just refers to the tubular nylon that holds everything together after it's deployed so that your like nose cone doesn't fly off by itself. And it actually attaches everything to the parachute. And typically that'll get attached to your rocket using something like U-bolts. I know I-bolts are also pretty popular. The important thing is that it's typically a best practice to use something metal that you can bolt into one of your bulkheads. Can I not? There we go. So in terms of buying components, if you do want to do this yourself, I'm actually, to kind of go over this quickly, I believe the largest vendor of rocketry supplies is Apogee Components. But you can find a lot of the hardware and adhesives that you typically use just at a hardware store. I know like 2 days ago, I just went to Home Depot and bought some epoxy, which the standard like 2-part epoxy is generally your best option for assembling things in a rocket that need to stay put. So for example, like affixing your fins in place, affixing bulkheads. More than anything, I recommend doing a bit of research yourself to figure out where the best deals are and find the right components. One thing that you should definitely be aware of is that a lot of common components are sold by rocketry vendors under not standard names, and they sell them for a higher price. And I give an example, shear pins. Rocketry vendors will sell them as shear pins, but you can buy them as nylon bolts from other places. I'm going to quickly just tab out of here and into this tab. Can you guys see the Chrome tab I have open? Okay, that's good. But I just have a bunch of various shops just open to kind of quickly show you. Apogee Rockets just has a ton of things, rocket motors, launch accessories. Where are the actual supplies? Buy tubes, parachutes, etc. I believe these are the tubes that AIAA buys, which AIAA I know buys them in bulk for very cheap. I know another one, Lock Precision. They sell cardboard airframes amongst other things. For parachutes, there's Sphere Shoots, which is the one USLI buys our things from. The woman who runs it's pretty nice from what I've heard. You have stuff like CS Rocketry, which sells a lot of rocket motors and other such things. I think we bought a fair amount of motors from them. And to kind of show you what I was talking about with the shear pins, you can see Apogee Rocket sells, 440 shear pins for a 20 pack for like $556. But if you go on a website like McMaster Car, you can buy 100 of them for $688. Which this might not be the best example because I don't think any of you need to buy 100 nylon shear pins. But this still stands. You should always be mindful and like do some research to make sure you're not buying something for more than you have to. And then also there's Bluetooth, which we've used a lot in high power rocketry. Generally Bluetooth is kind of overkill for L1 rockets, but I don't know. Back to the presentation. The next thing I wanted to bring up was making your own parts. You could see here our fin can from this year. It is definitely possible to 3D print parts of your rocket, or make them using other techniques, whatever other tools you have access to at home. But it's important that if you're ever making your own parts, you need to be able to verify that they will work, either through testing or simulation or something. I know I made this mistake when I launched when I tried to get my L2 rocket, and I 3D printed my own nose cone, and I know Joe predicted pretty much exactly how it would fail, but I launched it anyways, and the bulkhead I had made for it was too thin, and it ripped off the recovery harness, and I don't know where the upper airframe of that rocket went. So I have to build a new one and fly again sometime soon. So if you do make your own stuff, make sure it works. Don't just rely on it seeming like a good design. So on to construction. Just to build some building advice. I mentioned this a bit earlier, but epoxy is the adhesive of choice here. Typically, you'll have your bulkheads and centering rings kind of go over, and the best way to get them to stick in place is epoxy. There are other adhesives you can use, but it depends on the situation and can depend on the material. Oh crap! Dang it! Sorry, I'm trying to look at chat. Oh, it's okay. Same deal with U-bolts or I-bolts for your recovery harness. You can like do other things, but things like U-bolts and I-bolts are just a reliable way of making sure your recovery harness stays attached to your rocket. Another thing, when you're actually tying things onto those U-bolts and I-bolts, make sure the knot you tie is secure and a good knot. I know my personal favorite is the bow line, but there are many other options. The most important thing is that when you pull on the nylon, the knot should get tighter and should not come apart, for obvious reasons. Finally, when you are tying your parachute when you are tying your parachute to your harness, you need to make sure that it's tied in such a way that when your parts are all swinging around on the harness, they aren't going to hit each other. To kind of explain that a little bit more, typically, what you'll want to do is, layer the nylon out and place your rocket and your upper airframe or nose cone or whatever is going on the other end of this nylon recovery harness, and make sure that the nylon can tie to them, and then tie your parachute at a point where while both the lines are straight, they won't hit each other. Which that might be a little hard to explain without me showing you, but if people want some more explanation, I can always try sketching it out on something. So another thing, just common mistakes that happen. As for what Kirsten said, we can do that in just a bit. One of the things I see a lot is fins extending below the bottom of your rocket. So you can see on the lower one, on the lower picture on the right, you can see the fins extend below the bottom of the rocket. And this can be it makes sense in some situations. You can make larger fins. They can have more surface area, get more stability. And it also makes it cool because then you could stand your rocket up on them and it looks really cool to display it. The thing with that though is oftentimes if you're using 1/4 inch plywood, if you land directly on a 1/4 inch plywood fin, there's a good chance that you could break it. And if you break your fin, then you won't get the certification. Your rocket needs to come back in a state in which you could refly it. And so what I advise is doing something more like the top picture, where you could see the way the fins are positioned. It's very unlikely that the fin is going to hit the ground first, unless it comes in at a crazy angle, which it won't. That way, the bottom of the airframe is the thing taking the brunt of the force, and not your flimsy 1/4 inch plywood fin. Obviously, you can get away with, having them extend below, but you just need to make sure that the material you're using is strong enough to deal with impact. Another thing, make sure that your parachute is attached close to the harness. Make sure that your parachute is attached to the harness close to the nose cone, just to make sure that it does actually come out. I believe that was what caused a lot of the L1s that flew on the day Kirsten got her L1 to fail. Correct me if I'm wrong. That might have been a slightly different mistake. Kirsten, were you going to say something about that?
No, I was just going to say it was between that and then some of us just rolled our parachutes weirdly.
Okay.
Because the NAR guys made us re-roll them.
The NAR guys made you? That's weird.
Yeah.
Oh, that's another thing is when you're packing your parachutes, you need to be able to pack them correctly. I don't know if I can demonstrate this right now because I don't have a parachute on me. But if people are interested, I could probably try to make like a video of me folding a parachute sometime. But yeah, that's something that's not too hard. And if you're at a launch site, you could probably find someone who's willing to teach you how to fold a parachute. So before we continue on, is there anyone who has any questions about all that stuff I have been saying? Neat. Okay. So we are going to tab over to OpenRocket. And here you can see I have loaded up. This is actually the OpenRocket file that I used for my level 1. And I just want to, before I start going into, the actual specifics of like making the rocket, I just kind of want to step through this design, kind of show you what all the components are doing. So to start off, just in this box right here on OpenRocket, you have your design tree, in which case you have the rocket at the top, and then you have a number of stages, which I'm not really going to go into stages right now because in our case, we only need one stage. And so you have the stage, and within that, we have all the components going from top to bottom. So you can see I have the nose cone. I have that 3-inch inner diameter craft tube that AIAA has. And within that, there's the shock cord and the parachute attached. And OpenRocket, you don't need to like specify exactly where everything is tied. But yeah. Continuing on to the most interesting part of the rocket is the fin can, which generally the fin can refers to all the structural components at the bottom of the rocket that do things like hold the fin can on and the motor tube in place. And typically, USLI, we've been doing all these like fancy fin can designs where we have the like nylon X brackets, but when you're building something for yourself and also at these lower powers, something that fancy isn't necessarily needed. Weird way of saying it, but that's usually overkill. Typically what you'll want to do is something like this where you have a number of centering rings. So basically each of these rings is a 1/4-inch thick plywood bulkhead with a hole in the center of it that the motor mount goes through. And from that, you have, these three that are all equally spaced, and they kind of hold together this bottom section of the rocket. You'll want to have them epoxied in place. And within going through all of them is this motor mount, which is another, tube. This could be another craft tube or cardboard tube or something. The important thing is that it has an inner diameter that snugly fits your motor casing. But yeah, basically what you do when you actually go to fly this is the motor casing goes in there, um, and that's what holds the motor casing goes within the motor mount or motor tube, as it's often called, which is held centered by the centering rings and firmly in place. As you can see, the fins here, they also slot into the fin can, hence the name fin can. And you'll typically also epoxy them in place. You'll usually, the other thing, to actually keep them firmly attached, uh, you'll typically do what's called a like through wall fin. Um, Oftentimes, for those of you who built like model rockets, oftentimes what you'll do for those really small ones is just glue the fin on directly to the outside. And on these larger rockets, that doesn't provide enough structural support. So what you'll do is you'll have a shoulder that goes all the way down and touches the motor tube on the inside. So you can see this kind of blue shoulder that goes in here. That holds it very firmly in place, and that shoulder gets epoxied to the inside. Finally, uh, I want to draw there's some components which I don't have modeled on here. For example, you can notice that I don't have any U-bolts or anything. And Open Rocket, you don't typically, there's no like U-bolt component, but what you can do is add a mass component. And a mass component is something that's doesn't really, within Open Rocket, it doesn't have any particular aerodynamic properties or special effects. It basically is just there to stand in for some known mass, such as your hardware mass, or possibly if you have a payload or a flight computer that's in here. You can see you can specify the actual size. And finally, perhaps most importantly, is motor retention. It is very important to have something to secure your motor so that when it burns out, it doesn't fall out the back of your rocket, especially if you're using a motor ejection charge. As I mentioned earlier, how some motors have a black powder charge at the top to deploy parachutes. One of the things that can happen is if your motor is improperly secured, the charge can go off, and instead of deploying your parachutes, you end up shooting your rocket motor out the bottom. And that's bad for a number of reasons. Yeah. So I guess another thing to note very quickly, I realized I forgot to mention this during the construction, is when you are using epoxy, make sure you use a good amount of it. You need enough to firmly attach things, but you don't want enough so that it's getting all blobbed up everywhere and making a huge mess like certain other people. Yeah. Okay. And finally, another thing that's not modeled on here is the actual shear pins themselves. And basically, the shear pins are just typically nylon bolts that go in, into the shoulder in between airframe sections. Basically, places where you want the rocket to separate. So you can see here the shoulder on the nose cone. You'd have maybe 2 or 3 shear pins holding it on, and that way, once it fires off, once the ejection charge goes off, the force is such that the pins shear and the nose cone is able to break free. One of the important things is your shear pins. You should be able to like hold your rocket by the top and not have the shear pins shear. If your shear pins shear in that case, then you don't have enough or aren't using strong enough shear pins. Your shear pins need to be able to hold the rocket together at least while it's in flight. Yeah. So now to actually, are there any questions about, rocketry components and how they're looking on the actual rocket? Cool. So now to actually talk a bit about OpenRocket itself, I'm just going to start off by just kind of going through the UI down here. So in OpenRocket, you have this main UI window that shows the rocket that you are building. You can see the dimensions up here and along here. And in the corners of this window, you can see different parameters, such as the total length of your rocket, the maximum diameter, its mass. Over here, you can see the stability characteristics. So you can see the location of the CG and CP, which are marked here. And you can also see the average stability of your rocket. In this case, mine is 2.61 cal, which is a pretty good number. And you can also see down here the simulated apogee, maximum velocity, and maximum acceleration. And those depend on the motor configuration you'll have, which I'll get into in just a bit. But yeah, seriously, 2,000 feet is that's pretty decently high for a level 1. That's nice. Up here, as I mentioned earlier. Oh, actually, before I continue, one of the neat things, I don't think this is. You can do alternative views of your rocket, so you can see like the back view. They also have a 3D view, which is, if nothing else, just interesting to look at. If you want to get really into it, you can like apply decals and whatnot, but there's not that many reasons why you'd want to do it other than just making some cool renders. If any of you are curious, they do actually have a photo studio, which I only figured out a bit ago. Neat feature, not particularly useful for most situations, but it's pretty cool to get some pictures. So up here, as I mentioned earlier, we have the design tree and all the components that I have. You have these buttons for manipulating the order and whatnot. There's the new stage thing, which I mentioned earlier. I just wanted to make sure you guys are aware of the button, but we won't need more than one stage. In terms of components themselves, you have a variety of components to select from over here. Some probably the most important ones, nose cone and body tube. I think those are pretty self-explanatory. Can't really fly a rocket without them. Transition, basically that's a segment where you're transitioning from one diameter to another. I don't particularly recommend doing this for your very first rocket, but it can be something that's neat to do eventually. Sorry, I'm trying to respond to someone messaging me. Okay. And then you have, they don't use the word fins on these, but you have trapezoidal fins, elliptical fins, and freeform fins. Basically, these are just different shapes of fins you can use. Trapezoidal fins are probably typically going to be the easiest to uh, cut out of wood, just because they're very simple. Um, Elliptical fins are probably going to be harder, since if you're doing it by hand, you will have to follow a curved uh, line when you're cutting. And freeform fins, you can see the ones I have on here are freeform. Um, Basically, if you double click on any of these components, it brings up the component options, uh, which allow you to specify a number of things. Like it changes depending on each one, but number of fins, fin rotation, fin cant. In this case, uh, you can also change the name and specify materials, paint finish, etc. If you go to shape on the freeform fins, here you can actually edit uh, the shape, which you do by specifying a number of points. You can drag points, click on the line to make new points. I believe you can, oh, there we go. Control click to remove them. Freeform fins, I think, are probably the most fun, but you have to make sure that the fins you're making are manufacturable. There's also tube fins, which is another thing that you probably won't want to do on a first rocket. I'm realizing I also didn't specify this when I was talking a bit earlier. One component I neglected to mention was your actual the rail buttons. So you can see here, OpenRocket has launch lugs, which is basically a small tube that goes on a launch rod, and that's typically used on smaller rockets. That's necessary to actually get things flying, to actually hold it onto the rod while it takes off. For larger rockets, for high power rockets, you typically don't see launch rods. You typically see launch rails, which the distinction being that launch rails are a lot more sturdy and are typically made out of aluminum extrusion. And rail buttons are basically a small little button that's screwed onto the side of your rocket that slots into the slots on launch rail. You'll want 2 of those. You can have 3, but there's typically not much of a reason to do that. Your best bet is to have 2 to make sure it's aligned well. Continuing on through, we have the inner components next. You can go back to the side view. So inner tube, basically, that's any tube you have on the inside. Most commonly, in this case, I have a motor tube. That is a tube on the inside of the rocket. And there are some other situations, but in this case, we want to go through and make sure that convert this to millimeters. You'll notice the inner diameter of this tube is 29 millimeters because it has to fit a 29 millimeter motor. Continue on. There's also couplers, which are similar to the inner tubes, but they're basically to hold together 2 sections of airframe. For example, if you look at the eBay on our full scale, you'll notice that there's a section of inner tube on it that slots into the lower half of the rocket, and that's what actually holds it together. You put shear pins through that inner tube. Continuing on, centering rings. Basically, it's a bulkhead with a hole with it, so you can put typically an inner tube through it. Very important to holding your rocket and holding your motor in the correct orientation. A bulkhead is essentially just a wall within your rocket. They can be very useful for mounting things to, or just to provide actual structural rigidity. They're also engine block, which in our case, that's something only really used in low power model rockets. It's not something you really need to do. And finally, you have parachutes, streamers, which is again another typically low power rocket thing. Shock cord, and finally the mask flow I mentioned earlier. So once you have all those, as you place them in, you'll typically, add them, double click on the component, and then you can do things like change the shape, the parameters, to get, the shape of whatever component you're planning on buying or whatever component you want to make, to better match the actual what you're actually building. Um, yeah. Uh, one important thing to go over, just in terms of options, is your parachute, um, because that has a big effect on how the simulation is run. Um, so obviously you have your diameter select, um, but if we go to this bottom right hand corner, we have the deploys at thing, which determines when your parachute is deployed. Uh, if you're using a motor black powder charge, that'll happen at some number of seconds after launch. In this case, my motor sets off a charge 11 seconds after launch. If you're doing electronic deployment, you'll typically want to do apogee, because an actual computer detects apogee and is able to fire right at apogee. Yeah. And so as you're kind of designing this, you'll want to keep an eye on the stability. You may need to change the size of the fins, change the length of the body to kind of get it within a good range, um, to make sure it's not too low or excessively high. But yeah. Any questions about just building things in OpenRocket before we move on to me showing you some of the simulation stuff you can do? Okay. And just to kind of give you guys an idea of where this is going, after I do the simulation stuff, I'm going to, stop recording, and then I'm just going to have some time for you guys to try doing this on your own. And, any of the more experienced people who's around can, kind of help out where needed, provide guidance. In any case, moving on to the actual simulation, we have these three tabs up here. You have the design tab, which is what we've been on. Motors and configuration is the next one. And so this one is a very straightforward. This is basically just deciding what goes into your motor tube. So you can see, I'm just going to make you can see the motor configuration I have right here, just as this is something I already said before, but just to show you how to do this, I'll make a new one. So first time you do this, you just hit new configuration, double click on that, and you can see OpenRocket just pulls up this huge database of all these different kinds of motors. And you'll typically want to kind of sort things through. You can set a minimum and maximum impulse. So in this case, I just want a H motor, so I'll just stick it at H. Motor dimensions, you can go through, change these, change what manufacturers you want. Currently, I only have CTI selected, and go through and, all these have different properties like the total impulse, the length of the motor, the diameter. You have to make sure it's the right size. But yeah, uh, once you find a suitable L1 motor, you can double click on it to select it. I'm just going to pick this H237-SS for just as a demonstration. And you can see it actually puts the motor in there. That's what the gray thing is. It's the motor. And yeah. Okay. Continuing on to the actual flight simulation. There's another case I have. I believe it. Yeah, so it seems like it automatically made the simulation for me. Basically, the simulation is just, it lets you set parameters and then just computes its flight. And so if you looking at these, you can see this one's red, this one's empty. That's just to indicate the status of the simulation. Red just means something has changed since it was last run. And so you'll typically want to run it again. Just if you hit run simulations, it just runs all of them. I believe this one means it's not configured or something. You can see once I hit run simulations, it turned green. You can also see I have a small check mark next to it, just indicating that it's all good. If there's something wrong with your simulation, like it predicts that your rocket will go too slow, or that it's going way off course or flipping upside down, then that'll change to a little red X. In any case, you could see in the simulation, you can specify all kinds of things like average wind speed, wind properties, atmospheric conditions. Usually you won't need to mess with too much of these, like particularly launch site longitude and latitude is not something you need to mess with much. One thing you do often need to change is the launch rod section. You'll typically want to figure out the length of the rail you're launching off of and actually put in the correct size. You can see the default is kind of short, only 39 inches. Typically, they're much longer than that, and so it's important to change. Does anyone here know off the top of their head the length of the launch rails that they have at Lake Winnipesaukee or in Vermont or one of the other sites we visit? CMAS, maybe 8 feet. Okay, yeah. So you can see it's, if I change this to feet, you can see it is really short, and that'll have a big effect on your off the rail stability and the like. So then you just hit simulate and plot, and then it brings up this thing. This is just a thing that lets you decide how you're plotting it, which you can experiment here and change the x-axis and what's getting plotted. But typically, these three right here are the most important ones you'll want anyways. So I'm just going to go ahead and hit plot, and you can see classic rocket simulation, the altitude as it goes up, and you can see the different events and how they affect things. Yeah. In any case, so just looking at this, this looks like a pretty good flight. You can see it flies up to a reasonable apogee, and descends at a reasonable descent rate. It's always important to look at, how fast your rocket's going. And Open Rocket will like give you warnings if your rocket's descending too fast, to like kind of indicate you need to like mess with parachute sizes or something. Just to quickly show you what that looks like, just so you have something to go off of. Change this to like a 12-inch parachute, which is very much too small. Oh, I need to select both of them to hit run simulation. No, I guess maybe it isn't too small. Is that? Huh. Minus 50 feet per second seems excessive. Okay. Well, in any case, oh yeah, you can see your ground hit velocity right here. 51 feet per second is a little aggressive. You'll maybe not want to do that. Yeah, I think 14 is probably still a little fast, but it's not terrible. Yeah. In any case, I'm going to kind of finish up here.
Max,
Yes?
sorry, did you want to tell them about optimum delay?
Oh, yeah, that's a good idea. Optimum delay is, yeah. So, yeah, I guess in that case, I'll just quickly go through all these different things, just from left to right. You have the name of the simulation, pick whatever name you want. The configuration, this is just indicating which motor configuration from this tab it has selected. Another thing is velocity off the rod. That is basically saying when your rocket leaves the launch rail, how fast is it going? You need to make sure that this is high enough, because if it's too low, then when your rocket leaves the launch rail, it won't be traveling fast enough for the aerodynamic forces to actually keep your rocket stable. And I know the NASA for USLI requires that you have to be going faster than 50 feet per second. So, you can see these two values, 58 and 100, are perfectly fine. Apogee, obviously the predicted apogee of your rocket. And next, velocity at deployment. This number you want to be as close to 0 as possible. Basically, this is how fast your rocket is moving when your parachute deploys. And the reason you want it to be as low as possible is because the slower it is, the less forces are going to be exerted on the recovery harness, just because it won't have to slow your rocket down as much. And so you'll typically need to like mess around a bit to try and get it lower, pick an optimal motor, the like. Now the one Kirsten was mentioning, optimum delay. This is something that this doesn't necessarily apply to electronically deployed charges, but this is really important for if you're using a motor deployment charge, because typically what will happen with the motor deployment charge is they come with a set fuse length, but the actual length of the fuse can be reduced using typically it's called a delay drill or a delay bit. I don't know exactly what they sell it as. Basically, it's a drill. It's a little drill bit in a special housing that makes it really easy to precisely shave off like an exact number of seconds from your delay charge fuse. So I know, like, for example, if I buy a motor that has like an 11-second fuse on it, but the optimum delay, that is, when the optimum time to deploy the charges is 8.3 seconds, then I need to use the bit to shave off you do 11. Usually can't do like fractions of a second. So I don't know, I'll just round it to 8. You take like 3 seconds off to get it, and that'll help reduce the velocity at deploy. So if I go back here to parachute and change this to 8 seconds. The simulation. Oh. Okay, I'm actually not sure what I did there. Can someone tell me if I'm explaining optimum delay wrong?
Isn't the optimum delay from the motor burnout to
Oh, it's from motor
not
burnout.
from launch? Yeah.
Oh, okay, that explains it.
So the 11s, I guess the motor burns for like 3 seconds probably.
Right. Okay. In that case, yeah, you'll want to look up what motor you're using, and it'll typically tell you how long it takes to burn out, and then you can then from there determine the actual amount to shave off. Kind of finishes off. You have max velocity, self-explanatory. Max acceleration, same thing. Time to apogee, how long it takes to fly all the way to apogee. Maybe I just should have rounded it to 9 seconds. I don't know. You have your flight time, and then finally your ground hit velocity, which you'll usually want to be something like 12, 14 something feet per second, so that when you actually land, you don't break your rocket on landing. Okay. With that, are there any questions? Rad. Okay. So what I'm going to stop recording now.